my friend and MVP colleague, Damian, the first speaker for today, is ready. Let me introduce Damian to all of you friends. Damian has more than 2 decades of experience in software development, and his bio is quite simple. He has real hands-on experience with a lot of different variety of projects. And we asked Damian that, why don't you give a real world session, the projects that you have been doing. Can you share your experiences and notes from the field with our audience? And he has come up with this topic that he's going to deliver now, which is real life machine learning projects, advanced linear regression consideration. I have no idea what this means. And that is why Damian is here, and he is going to talk more about that. Damian, over to you. And thank you so very much to join us in this virtual symposium.
Okay, thank you very much for invitation. It's really great pleasure because I've been so far also a participant and lecturer during the DPS summit past 2 years. And I will have my session also on December. And this will be something really new, as you said, because what I'm going to present will be about quantum computing, something which will be, very important in few. I don't want if I want to say in a moment, but in a few years, we hope the quantum revolution will be, and quantum computing will become something more and more natural for us as developers and users, because there is a lot of things we can benefit from. So this will be on December, but today I was asked to talk about machine learning. I gave a workshop last year about machine learning during DPS summit, and it was a lot of questions about some kind of what's behind the algorithms, what is the math, why the algorithms works that way. So I decided to prepare a session about linear regression. And the reason I'm going to talk about linear regression is because this is one of the most known, but the most known algorithm in the world. So you can even imagine how it works without having too much background. But I really like this algorithm because it explains a lot of complex machine learning features, and sometimes when you talk machine learning language, you think that there are important information that you should be able to translate to your language, like some kind of definitions. For example, why should you care about the number of experiments, and why should you rather try to compress the number of features? And this is exactly what you can derive from machine learning mathematics. I try to keep it, on a. It will be at some point kind of advanced session, because I'd like to explain you why it works the way it works. And at some point you will see that there will be some mathematics introduced, but this is machine learning. At some point you have to play maths here. And I'm really happy that Sandeep will have a session right after me, because feature engineering is one of them. It's really state of art. It really requires a lot of knowledge, and you have to have a lot of background, and you have to know the business. So I mean, what you do to make sure that you can do the feature engineering. That's one of the most important part of the process, which I will describe just in a second. So because I had I reserved 2 or 3 minutes just to explain you what a feature engineering is and how should you use it. But it's in my mind that there is, that if you would like to, if you have entire day, then it's okay. But one session will give you a very, very good introduction. So it's very good that Sandeep will start right after me. So I am Damian, and I am speaker from Poland. It's the afternoon here, and I'm very happy to be with you here. I work for UVic, where I am responsible for the projects where there is a data platform involved, and there are a lot of them, starting from a very typical projects when you just build a database and some processes around this, and the more complex projects when we have machine learning introduced as well. So if you would like to catch me, then just drop me an email, or let's talk on the Telegram. If you have questions, I will be more than happy to talk to you and answer them. I have been MVP since 2009, so it's quite a long time, and I'm very happy to be in the team because this gives me the opportunity to speak on this event and be quite close to the technology. So don't forget about this event, which will be 72 hours. This is just impossible, and I'm in shock that Amit and the team is going to, to organize something very, very unique across the world. So don't miss it. There will be a lot of MVPs, people from Microsoft and other experts, field experts. So, and now I think that there is a good price for it. So it's time to join the and be at this event as well. And I would like to invite you to my session about quantum computing. So I will share you the latest information about quantum computing. I'm going to explain you how this quantum computer works, and what's more, I will run demos on the real quantum computer during the session, so you will see it. There are several quantum computers across the world, so I will explain you how it is to write a program on quantum computer and run it real time during the session. And we will examine a pretty standard, and yet most important experiment, which is the most important one in terms of quantum systems, which is quantum entanglement. So please join me on December. Today I'd like to talk to you about simple linear regression and then go to more generalized problem when the linear regression is no longer linear and there is something else which is linear but not the features. But I will start from something which I think we need to spend a minute or two, which is machine learning 101, which means I'd like to tell you what a machine learning actually is. So think about it that way, that to have a machine learning, you have to have two components. One is the machine, which could be anything which has computational power. So it could be a computer, it could be a robot, it could be your phone, whatever has something where you can run a program. So that's the machine. And then there is a learning. And the learning is a process when you have an activity, or you can, for example, look into some patterns and to try to recognize some patterns. And we as a people, we try to be very creative. So we don't want to do boring tasks. And that's why people invented machine learning, to say, okay, machines are designed to perform the boring tasks, so we can think about something else. We can invite quantum computer, for example. So that's why people invented machine learning. So because machine is something which has no life in it. So you can give a boring task to machine. So for example, to learn something, to follow some algorithm, learn some rules. But there is a very important distinction, that this is not something you can write as ordinary program. So if you think about program which has a lot of loops, if statements, while statements, this is not machine learning. Machine learning is something when you try to find what is hidden in the data. So you try, usually it's a very, very complex process. It has a lot of inputs. It can have a lot of outputs. Typically, it can be one output, but it's not the case. It's not mandatory. So the process is so complicated that you cannot build a static program. Static in that terms that you compile the program, the program has all instructions in it, and by instructions I mean something like this. So imagine that you have, for example, an object which has 20, for example, 22 features. So and one output. So you have to analyze 21 features, combination of each other, to generate an output. And I gave you a session about this last year on DPS, and I made, I calculated how many lines this program should have, and it turns to be 10 to the power of 19th if you would like to resolve all the combinations. So it's not possible to write a program like this. That's why we go to the machine learning, because we can build a black box, which is the model. There is an algorithm which can work somehow and generate the best fit to the problem. So this is so-called data-driven prediction. So we don't have a static program. And what's more important, those algorithms are able to learn, so they can adjust to new data and they can adjust their parameters slightly. So this is very important. So, machine learning process is not that easy thing, but at the beginning, you have to ask the right question. And that's the first thing you have to do. Because if you don't have the question, so you don't have the goal you'd like to resolve, so the machine learning process is not important. But I assume that we can say, for example, we know what we'd like to do. For example, I will give you a demo about sales. So you have a budget for marketing, like you'd like to buy some ads on Facebook, Twitter, on TV, radio, and then you'd like to measure the sales of your items. So in that case, for example, you'd like to say that you'd like to have the probability that, very high probability that, for example, if you invest $100 million with 95% of probability, you will sell, for example, 2 million of items. This is something you can measure. So the model has to allow you to have this probability as a goal. Then there is, if we decide this part, then we move to another part, and this is something that Sandeep is going to talk about you. So this is the data preparation. There is a lot of things happen there, and telling the truth, the preparing data is like 80% of the entire process. So you have to be a very patient person. You have to love your data. You have to know what to do with them, how to prepare them. It's a really state of art. There is a lot of formal knowledge behind this, but there is a lot of things that you have to have a lot of experience. So it's good that the next lecture is Sandeep, and he will explain this in more detail. Once you have the data in place, data that is prepared, then you can go and say, okay, which algorithm should I pick? And it all depends, and I will tell you in a moment why it depends. But mainly it depends on the type of machine learning process you choose. So for example, you do classification or regression, and let's stop that way. Then you have to train the model, and you see that your model has some metrics, for example, the precision, so how good the model is. If the model is good enough, so it has the required, it can ask to the question, then you can test the model. But you can specify more than one algorithm. But today we just concentrate only on linear regression. But typically we pick all of them, all algorithms that are good for this specific process, and we pick the best one. Once the model is tested, then we can use it on production. But just to make sure that you understand what is behind all of this, it's a lot of maths. And the more you love maths, the better data scientist you are. So you have to have brief knowledge of statistics, linear algebra. This is something I'm going to use today. a probability theory. It will not be in our topic. There are algorithms that, for example, naive Bayes, which is a probability. But for sure, we take a look into mathematical optimization. But I will not get that deep into this. I will just tell you what kind of optimization we'd like to do, and I will give you the solution. Because in general, this might not be that that easy. So I briefly told you about one thing, that we have two types of machine learning processes, and I already mentioned that. So you may think that, okay, if something is linear regression, that we are going to have a regression machine learning, which is under supervised topic. And supervised means that you have, you know your data set, you can label each of the column, so you know what all the columns are, so you can name them, you know the purpose, and this is so-called supervised. You know the input and you know the output. And you may think that, okay, it looks very good because I know my data set, but the problem is that if your data set is big enough, for example, you have 200 features or you have 1,000 features, so input parameters, then there is a problem that you can, for example, make a mistake with naming them. And the output from the model will not be exactly what you like. And I think Sandeep will tell you something about this, how you can reduce the number of dimensions. So, you know, it's hard to imagine that you can have a model which has 1,000, 1,000 inputs, and how you can reduce it up to 2 or 3, to reduce to 2 or 3 dimension space. If we think about unsupervised machine learning, it's something different. You can have the same data set, but you do not name whether this is input or output. The system has to find out the hidden knowledge. And this is, the combination of those two machine learning types is now something that we think it's the solution for most problems, because in unsupervised, you are trying to have information about your data, which you probably don't know. So there is a hidden information in your data, which most of the time is right. And you have to find the missing information exactly in the data itself. So you can't just name the input or outputs, you just put the data as it is, and the algorithms has to find the proper solution. And that's all. I'm going to close the presentation. I'm not going to show it to you anymore. What I'm going to show, hopefully you will see my screen, because I'm going to draw something for you. I mean, I'd like to briefly introduce you why we need a lot of maths, and then I will do a demo in the Jupyter notebook, so you'll see exactly how it works, and I will explain it in more details. So let's start with something which is very, very easy. And imagine that what I already told you, imagine that you have a new phone and you would like to sell it. So you'd like to put it into market. So, you can imagine if you are Apple, or if you are some other company like Samsung or another big competitor, you can just go to market and probably you will sell. But the question is if you can do better. So what you do most of the time is that you'd like to have some kind of budget, and you would like to say, okay, I'd like to see a correlation between the budget spent and the items sold. So you can draw a very simple table at the beginning. It will be oversimplified, but this is what the regression can be at the end. So you can say, I'd like to pay for some advertisements, and we can say we don't know where the advertisement go. It could be on Facebook, on Twitter, it could be on social media. You can buy advertisement on TV, on radio, wherever you want. Of course, we will divide this. In real life, you would like to divide this into smaller groups. But as of now, we can say that this is total budget I spent on my advertisement. And of course, I'd like to have information about my items sold. And you can imagine it will work that way, that, for example, if you spend 50 millions, you can spend 25,000 or whatever number of items. And you can say that for, if you spend twice as much, for example, you sold 53. If you spend 150, you sold, for example, 78, and 200, and you have 1,000 items spent, 100,000 items sold. And let's do one more. It's 250. So you have number like this. So you see, there is a clear correlation that you can say that you see something in the data. So the number of, so there is a correlation like this. So the, not that way. So the items spent, so the items is somehow correlated to the budget. So what you should do is you should try to draw a line, straight line like this. So here you have the advertisement number, so the money you spent, and here are the items. And you can say that you spend some money, which is like this, and you can put the numbers up to 250. And then you have the numbers of items sold, so it's 25 here, up to 130. And you can say, I have, my data is like this. So the question is, if there is any mathematical formula which you can derive when you can say that there is a best line you can draw. What I mean by this? What will be the best line? Will it be that way? Will it be that way? Or maybe this is the best line? We don't know yet. So there is a lot of questions. You can, telling the truth, you can generate infinite number of straight lines here. But how to find the best one? Because the best one, this will be our model, which will give you a prediction for the future as well. So what we can do, let me draw this picture one more time to give you the concept more clearly. So right now I will say that I have X value here, which is the budget spent. And from now on, I will be using the name X. And there is a Y. So this is the items sold. Sorry for this. Yeah, okay. And now imagine that we have some numbers here. So you spend some budget. There is also a number here and a lot of numbers. And you have your data points. I hope you see how beautifully my data points looks like. And the question is, what is really the functional relation? And you know the answer is pretty easy because you were at school. So at school, they told us that it should be something like this. There is an A coefficient times X plus B. And in you can find a little bit different, the naming convention here. It could be beta 0 plus beta 1, whatever it is. It is something, this is something which is constant. And take a look. I can draw a line like this. And imagine that for some reason, I think that this is the best line. I will introduce in a second, what does it mean for you, the best line here. But we need to think about where are the coefficients on this straight line. So how to find the coefficient A, this one, and the coefficient B. And it's very, regression is very simple at some point, especially if you have linear regression of one variable. So in that case, we don't have to think about too much, but try to do a simple calculation. If your X is 0, then your value of your function is exactly equals to B. So when you have X equals to 0, then Y is equal to B. So this is this point. So you can think that, okay, this part is B. And what is the business interpretation to this? So business interpretation is that you spend 0 money, so you don't even started your marketing, and you already have a lot of items sold. So this is This is, you know, the initial state. It is called intercept. I try to put the name here, intercept. I will send you this PDF after the session, so don't worry about this. Sorry, I almost can't write here, but this is the intercept. So in our example, business example, when you say, I'm starting my marketing right now, what happens if I don't spend any cent or any single money? How much I'm going to spend, how much I'm going to sell. You know, this is not how normal marketing works, because this is only the beginning information you have. Of course, you'd like to have this B coefficient should be bigger and bigger, but I will show you example when the B is negative. And in that case, it means that you have to spend a lot of money to see anything spent, which is like an initial inertia. But where is the A coefficient? And it looks like that if you can draw a line here, which is like this, so then you see a kind of slope. So the bigger the A is, the bigger the slope of the function is. And the slope is somehow proportional to this angle. This is the angle which we call theta. So you can say that my A coefficient is somehow proportional to this angle. And you know, from the trigonometry, this is right triangle here. This is right triangle here. So what you can do is you can say that my my coefficient A is proportional, is even equal to the tangent of the this angle. And the way we measure it is, you know, it's this coefficient is very important because it describes the change, the rate of change. So you can imagine a situation that you would like to measure if your change is from this to this, how big change is on the item sold. And this is exactly what the slope is responsible for. So you are going to measure the rate of change. And of course, as it is linear regression, the change can be pretty big. So you can measure, for example, like this. But if we make the, you know, our talk more general, we try to have the change pretty small, because, you know, if you perform smaller changes, then probably you will introduce a very, very small error. What else can we see on the line? This will be this is the last thing I'd like to show you on this particular line. So imagine we have something like this, that you have a point. So you see data point here in black, but imagine the situation that there is a budget which is 100 and 150, and you would like to say, okay, what is the most probable item sold number if I spend 140, so here. And it turns that this number is not in your data set. And this is the reason, and this is the way linear regression works. So it can give you the number for a given input. So you put an input here as an input vector, and you have the output. So it can generate a number belong to the data set. Oh, sorry, something is with my. Yeah, I hope you can still hear me. What I think just happened is my my headset was disconnected, but it looks good. Sorry for this. So take a look. This point.
In fact, your when your headset got disconnected, you were sounding better, Damian.
Yeah. Okay. So I can disconnect. I hope you can hear me now.
Yes, so, of course.
This point here, it has a coordination like it could be like x from the 140, and it has some value for x 140.
And this value does not belong to your data set. It is generated by by this linear regression. That's very important for us because then, it's a different type of the machine learning process because, for example, if you have classification task, then you do not generate a number. You generate information to which group you belong to. So, for example, you divide something into groups like this is banana, this is apple, and you can be only one of those. This is a dog, this is a cat. It's not a number. In regression, you generate a number which fits the best to your line. Sometimes there could be a case when you have situation like this. That was the line I was showing you in a moment ago. But we can have another line which looks like this. And this is the case when the B is negative. So here you will see the B is less than 0. So in that case, take a look. You have to spend this number of money and still you don't sell anything. That's very important. The B, the intercept value, is very, very important for us because in that case, it tells you how much you have to spend. What is the budget for your company to put a new model into the market without selling anything? So that's the risky part. You can say it's a high risk here in terms of putting some money here. So the bigger the B and the slope, then you have a lot of risk in that terms that you might want to spend a lot of money or time or whatever to see any effect. It's like an initial inertia. So you are giving a lot of energy, a lot of power, and you see the output is doing nothing. So the output is actually 0. You see, this is 0. On the y-axis here, you have still 0. So you have not sold anything. It's just 0. Okay, but that was just information that it's not, from the business perspective, it's sometimes very tough to, invest in something because you have to prepare a really good model. And what a good model is. I told you in the beginning here that you can, in theory, you can generate infinite number of lines. Which one is the best? Which one fits the best to your data? How do we call this? How do we name this? So in that case, what people thought we can do at the beginning, they were trying to find out something like this. Imagine that we have some numbers here once again. So we have data here, we have data here, and data here, something like this. And you decided that your best line is, it's almost a line. But there is a very good example of what I'm trying to explain you now. So the best line would be if this is the actual data you have, and this is the predicted value you have. So in this point, for X1, imagine that this is a budget you spent to sell some money. So you were thinking that you are going to sell 25 something, but your line says it will be, for example, 27 or so. Doesn't matter. But in this point X1, your prediction, we will call it Y1, and this is the prediction value. Sorry, this is the real value. The prediction will be in a moment. The prediction will be here, and the prediction is in this point, and we call it Y1 prediction. And you would like to think that the best line will be among all the points when the difference between prediction and the actual will be as close, the difference will be as close to 0 as possible. But what it is, how you describe this, so how you tell what it is. So this is the predicted, this is the actual, so this is so-called error. So you'd like to minimize error. But what kind of error you'd like to minimize? Take a look into values we have here. If you think about how I specify this formula, So the prediction minus the actual value. So here the prediction is greater than the actual value. So the error is positive. So it's greater than 0. So we have situation that error is greater than 0. In this case, we have the opposite. So the error is less than 0. And if you take a look into the data I draw for you, we will have all the time situation that the error oscillates. It's close to 0, but you know, sometimes it's plus, sometimes it's minus, sometimes it could be that it will be exactly 0. That's how we can build the function. But at the end, you have a case when you have plus, minus, something like this. You know, if you have a bad luck, if you sum it up and you say error in the point number 1 plus error in point number 2 plus error point number 3 plus, then the error will be 0. And the question is whether this is good or not. And of course, if you say it's bad, then you are right. And the reason is, think about error I'm going to draw for you right now. Take a look. I have a point here, which is like this, and I have a point here, which is like this. If you sum it up, so this will be the negative error. This will be the negative error. This will be the positive error. So if you sum those 2 points, the errors, they will still be 0. But you see how far the points are from the function. So the function is no longer, the best line. Or it could be the best line, but it has a lot of errors in it. So in that case, you can say, okay, summation of errors like this, it's just not what we'd like to have. So what you need to do is you need to make sure that all errors are positive. So how to do this? So positive error means that this point would have to go there. But you cannot change the value of the point, but you can change how you measure the error. And the best line will be in case if you try to minimize the error. So in that case, what you try to do, you try to minimize something like this, that you are going to sum the individual errors. You have n point in your data. So that's the number of points we have. And you try to do something like this. What I'm writing here, so I'm trying to take my prediction minus the actual value, and I'm going to square it. And this is something, if you put square, then if you have minus value, it becomes to positive, yes? So this is the way you are going to work with your errors. It will always be positive. It will never be 0 because of this thing. Yes, so plus minus. So this is something we'd like to remove. And this is what you see here. This is the first very important metric in machine learning linear regression, which is called RRS. This is residual, so something that's left, sum of squares. So this is our first metric, squares. Yeah, it should be like this, squares. I have to remove my this headset from here. Okay, good. So now we have our first metric. So we can measure how good our line is. So we'd like to minimize the residual sum of squares. But there is one more problem here, which is, imagine that we are now going into a little bit different example. So we, for example, have a function, which is a function like this. It's a function, very simple linear function x to y. And for example, the x was first measured in kilograms and y was measured, for example, in rupiah. And now you change the dimension. And now you say, okay, I don't want to measure kilograms anymore. I'd like to change in grams. And I'd like to, in that term, I'd like to switch my currency, for example, to US dollars or whatever value. So in that case, is your model still going to fit? From, you know, our feeling is that the measure, what you have here, it's still the same. Because, you know, 1 kilogram, it's 1,000 grams. There is a problem here because, you know, that you have to have a coefficient which transforms rupias into dollars or whatever other currency you have. So in that terms, your model, the coefficient you found, they will not be able to, you will not be able to use the same coefficients because, you know, in the model, if you write your coefficients once again that way, so it's, for example, we can say it's B plus AX. Something you have from data, it's this and this. And this is something, so those and those are just numbers, those are measures you have from data. So you cannot control them. This is something you have. What you can control is this. So the idea of finding optimal line is to find optimal coefficients. So our goal will be to find optimal A and B so we can minimize metrics. One of the metric is residual squares, sum of squares. There will be more, but whatever metric you would like to minimize, which is related to minimalization of errors, is okay. But if you now change data, especially like this, then the A and B is no longer valid. And you have to make another model. It still be a line, still be a linear regression probably. It will be linear regression, you know, because this transformation is static, it's 1,000. If you change rupiah to some other value, to some other currency, you will have also some static transformation, and that's all. So the model will be the same, but will be this model will also be, you need to find out proper coefficients. So that's the case. So you cannot just, you know, change the dimension and say that everything will be fine. That's one of the things, please remember about it if you do transformation like this. I would like to give you some other metrics before we go to the demo, which I think will be just in a few seconds. Let me just take a look into my notes. And you know, so far I was telling you that we'd like to find out trying to find out the best line. But you know, people in machine learning, they are a little bit crazy, and they think that if you find the worst model, then it's also okay. So you can always find, you know, the worst possible function that fits to your data. And this is so-called TSS, which is called total sum of squares. And we still have the same, you know, function. So imagine that we have points like we had previously, X and Y. We have the line, which is like this, and we have points. So the line, what is important, the line has to go through, you know, a point which is in the middle. So we can say it's a median or it's a mean value. It's a mean value. So you can say that I have the mean value here at this point. I have some data point nearby this line, but it's not the best line, you know. And then you can find that, okay, you have your data. So this is the prediction. This is the prediction you have, and you are trying to, if you put line like this, so the errors, you know, will be bigger and bigger, or if you go from the line like this. So you see the line introduces a lot of errors, and this is this is the point in the middle. So the TSS will work that way, that the formula is that you are going to sum from I up to n points, but you have then your your value, which is the actual value. So you will have the actual value, which is y, and the index is I, and you minus it from the, but take a look, the mean value here. So there is no index here. There is no index here. So this is calculated once, because you can say it's the mean value or it's an average, whatever it is. It's something which is in the middle of your data set here. So in that, this will be the worst model you have. And it seems to be that you can introduce another matrix, which is called R square, which is like that you have 1 minus RSS, so the best line over the worst line. And if you have this metric, you can say how it is called coefficient of determination, so how good your model is. And the idea is that if you put numbers here, the numbers can be from 0 to 1. Your model is good if it is close to 1. So model is good if you go close to the 1. The model is very, very poor if it is close to 0. And of course, if you go to the statistics, then you may say that something which is correlated, like, this is how your line is correlated with your data. Yes, so function is correlated with your data you have. So the bigger the correlation, the best the line fits. And how you can correlate, you have coefficients A and B. So the correlation should be, I don't know, 90%, 95%, something like this. If you have correlation like 50%, then this is not something you would like to introduce. And there are some more functions that you can play with, but I'd like to show you some kind of demos right now. So let me switch to the this one. Yeah, I hope you see at this moment that you can see the Jupyter notebook, and that's very, it's a very, very simple example. I was playing on the data set which is called Boston data set. It has to predict price of the house based on various parameters. So it looks like the input, the data set, it has 13 numbers of input parameters, and you are going to predict a price. So, in general, you can say, but this is a multivariable example. And so far, we talk about regression when we have only one input and we try to map it into one output. In this example, what we see is that we have 13 input and we try to map it into one output. And the more inputs you have, the more complicated the model is. And there is the state of art, which Sandeep is going to tell you about feature engineering, that you'd like to reduce the number of dimensions. And each of the input feature is like another dimension. So, you cannot visualize something which lives in 13 dimensions, but you can pretty much visualize something which lives in 2-dimensional space or 3-dimensional space. So this is the goal of the feature, one of the goals of the feature engineering. In our first demo, which will be dedicated to linear regression when we have one input, I will just pick one of the value. And without talking about what is this, right now I'm thinking it's a black box for me. I would need to spend some time on what the data is, but take a look what we have here. The data looks like this. We have number of samples. There are 500 samples. We have, those are the inputs. So we have information for example, how many crimes is on this region. Yes, the more crimes you have, the cheaper the house. You can think about it that way, yeah. But there are a lot of other things that are important. For example, how polluted is the air? What is the the average age of people that lives in that area? What is the pupil-teacher ratio? So the more the more teachers you have in this region, is the better. Yeah, something like this. And at the end, we have the price. So we will try to pick one of the value. But what I'd like to tell you right now is take a look here. Some of the values are pretty small inputs, and some of the inputs are pretty big. And this is the question you should ask Sandeep, how to fix this. Because I will tell you about multiple regression in a moment, and you will see that the number really matters. The bigger the number, the higher impact it has on the function. So we need to fix it. All the numbers should be on the equal scale. And this is something we will play with. So this is just information what we have in the data set. So you see 506 measures, experiments, and all are floats. So we have numbers there, so we don't have to do anything with it. No categorical inputs. We don't have to use one-hot encoders, nothing like this. We can describe the data set from the statistical point of view. So we can say, for example, what is the mean value? What is the standard deviation? Which means how we fluctuate to the left and right from the mean value. What is the minimum and maximum, and what are also the information about the quartiles? So where are the data? And if you think about it, typically we should have the mean value around this, in the middle of the in the data set. If you see that the mean value is nearby in the third quartile, that means that you have a huge data skew to the right, which is not good, of course. And you have to play a lot of transformation. There are some transformations to work with that. So this is how it works. And then, I try to visualize the data I have. And this is so-called heat map. And based on the heat map, I'd like to show you how the data is correlated. So, the bigger the correlation, the number should be close to 1 or -1. The 1 means that if you change the input, the output will go to the positive value. So like the price is going up. But the minimum correlation like we have here, so minus 0.74, means that if the value is going up, like crimes are going up, the price of the house is going down. So we have different types of correlations here. And this is the price, so this is the output, and in this column, so I'd like to take a look, what is the highest correlation we may find here? So if we see correlation like 0.36, that means that, okay, there is very less correlation here, and probably we will not have good function. So what we can take, for example, the RM, which is 0.07, like here, or we could pick 0.74 from here. But I choose this one, and I already started. So you see I have one input, I have one output, and what I'm trying to do now is in machine learning, you have to divide your data set into two parts. One, which will be used for training, and usually, but it's not always. Usually we take 70% of the data for training, and the remaining part will be for tests. So the test part is never seen by the model. So the model cannot learn from the test. It's just used to measure how good the model is. The 70% it's just a rule of thumb. If you have 200 million of experiments, you can take 10% to training and 90% for tests. It's perfectly fine. You have, the number of training samples should have statistical significance. So if you take, for example, 10 millions of rows out of 200 millions, it's okay. It's only, you know, it can be 5% of your data. It's still good. So I divided my data set into two parts. So into testing and train. And you know, this division has to be done properly. So you have to, you know, this function, which is a standard function in scikit-learn library, this function has to follow the data distribution. So it cannot take, for example, the minimum of 30% or the maximum or whatever. It has to follow the data distribution and peak data to make sure that the model will be able to capture the change, you know, the changes in data. Then I tested. I trained everything by the linear regression algorithm, and take a look. This is the result we have. So from here, you see that we have the intercept, which is negative, and we have the coefficient, which is the A. This is the A, which is 8 point something. This is the number. So you can see the slope. The slope is positive. So the bigger the input, so you can say if I change my input by 1, the output will be changed by 8.6. Yes, that's the interpretation, but the slope is negative. So you know that at the beginning you will have to add more and more and more to the input, and your output will still be 0. So that's what the coefficient says. And then I try to draw something for you. I mean some errors, and you can say how the data fits. So you can see I have data points. I have 150 data points in the testing, in my testing data set. And this is the price. And you see the value on blue is the actual line. And the value in red is something I predicted. And you see more or less it matches. Yes, you see it was able, this model was able to capture the trends. It not fits perfectly, who cares? But at least it is able to see the data changes, which I'm very happy from this. And then I was able to find out the, you know, the error. So you see I have the test value minus the prediction, and you see the error is like plus minus 10, whatever number it is. It could be, you know, it could be in thousands of dollars. So you can say that, okay, for this particular point, which I'm pointing here now, I should have paid less, for example, yes? And I overpaid $10,000. But in this point, maybe I was able to buy a cheaper house. So I am, in my wallet, there is still $40,000. So. But you know, we'd like to see how good our data is. So there is a definition of an error which is called mean square error. So the mean square error is the mean value of the squared error. So the definition, I will show you how, what does it mean that there is the mean words. So that's the RSS, but there is an item which says 1 over n. So the number of points you have. But you know, the R square, it's like, you know, 0.45, which means that I wouldn't play with this model, because, you know, you have, the correlation is 45%, which means I'm really unhappy with this model. But, you know, where the problem is, take a look. We have a lot of data here, which for sure does not fit. They do not fit to the model. The model is probably pretty good here at the, you know, in this part, in the part on the left, but it really doesn't play well on the right hand side. So how we can detect if something is wrong? It's so-called outliers. Outliers, those are numbers that do not, you know, fit to the data that do not fit to the line. And, you know, it's like, it could be, think about it, that a situation that you work for a big company like Microsoft, and there is a chairman, which is Bill Gates, and you try to compare his earnings with your earnings. So probably he earns a little bit more than you. And in that case, even if he earns, 10,000 more than you, it is not outlier. It's perfectly fine. Because in that case, he has a greater responsibility than you. He was, he was the chief of the company. So he has a lot of money, but also with greater responsibility. So it is not an outlier. An outlier would be, imagine the other situation, that you are trying to measure your heart rate. And usual when you do a training, it's like 170 beats per minute, but the measurements is like 1,700. So this is an error, because if you had heart rate like this, you'd be dead in a second. Yes, and you are still alive. So this is the outlier. And there is a lot of ways how you can define, how you can detect the outliers. And I will just show you this. Whatever is on red, or this is some kind of red color, those numbers are suspicious, and the one that really fits good to the line are on blue. So you see you have a lot of numbers that are, so the data points, the information you have, it's very low quality. So in that case, you have to look into your data more carefully before you do something more. So let me now switch back. I think we have a few more minutes. I will tell you more about the multiple linear regression. So just few words about this, because I have very interest. Oh, I told you about mean square error. So it's like something like this, that you have 1 over n, and then you have this sum I have presented. So it's like this. So the prediction minus the ith index of the actual value squared. So that's the mean squared error. Yes, that's the mean. And if we go to think about, there is a lot of information about correlation. So maybe you can pick another input, or maybe you can take more values. We have 13 inputs. And in general, if you think like this, so this will be now the general case. So, if you have more than one input, so more than one feature, then probably you will never have a straight line. So you will have something like this. So in that case, if you try to draw a line, straight line, it's just the line doesn't match data. You can find out another line. You can say, okay, I have something like this, which be, something like this. It's not perfect, but it's better than the red one. But you can then tell, I have better line, and it's like something like this. And I may ask you which one is the best one. And here you probably say, okay, the orange one is okay. But sometimes the line which fits the data best can lead you to very, very complex model. So in that case, you can say that your model is overcomplicated. If you have overcomplicated model, then for sure it will not, it will not play well on the real life. So you have to simplify your model, which means you have to simplify the number of dimensions. You introduce a little bit more error in that case, but in that case, your model is more general. If your model is too complicated, then probably you end up with something which is called overfitting. And I would like to tell you about overfitting a bit. In general example, the only difference between the linear part. Okay, what is linear here? It's still linear regression. I will tell you what's linear. So we can say that we have right now we have something like this. That's the output we try to predict. So it has the element which is B0. I call it those coefficients right now B0. Then we have B1, and in our example, it was like X. But now we have to do it more general, and more general case, it's really something complicated, which says, I have a function of X here, plus I have another coefficient B2, and this is another function of X2. And I can have a lot of things. So you can tell me, you know, and the function can be anything. It could be a square root, which is totally nonlinear. This can be like a cosine, which means you have oscillation. So the line will be, in that case, if you take, for example, this square root and cosine, it will go that way. So it's a periodic, but it's also going up. So you have some kind of slope here, plus the periodic function in it. So you have no control over what the function can be. So what is the linear part? And it seems to me that the linear part are only the coefficients. So in terms of linearity, think about the coefficients. And you can now change what you have here in something which is the matrix. You know, you can say that I have my output and I have my coefficients. It's B0, B1, B2, up to some Bn. And I have my vector of inputs, and it's called 1 because that's the first coefficient. Then you have function of the first element. You have another function of second element, and you can have, you know, almost infinite number of functions here. And you know, that's now we are entering, you know, the multidimensional world. And of course, what we'd like to do, we still like to minimize the error. And the error is like we described so far. So we'd like to minimize entry like this. So the prediction value minus the actual value. The actual value we have here. So what is the prediction? And the prediction is exactly, you know, if you take a look, what could be the prediction? So the prediction will be, if we have function, the prediction will be that part. The prediction will be that part. And we'd like to minimize this part, you know, and the best fit, if we can write it that way, take a look. If I could write it that way to simplify, what would be, you know, if you need to calculate the coefficient here. So if you are at school, you could write it that way, that a coefficient is y over x. Yes, it's simple as that. But think about it now. This is vector, and this is matrix, and you have a lot of things like vector and matrices and something like this. So you can't just divide something, you know, like you did in school. And for example, this y vector could be like, it looks like, so let me draw a coefficient. So you have, for example, 5 coefficients. So the number of columns is 5 and you have 1 row. Then you can have, you know, your matrix is 5 over 5 because the dimension have to play. So you know this output will be like this. You have to take left and right hand side, and you have 1 over 5 here. You have a lot of matrices and a lot of vectors. So in that case, this operation will not work. You have to enter linear algebra. And you know, you can find it almost every book, but the transformation will be written in that way. So you have to transpose, I mean, to do a pivot on your X, matrix, and you have to multiply it by the same. You have to inverse it, so it's -1. Do one more transpose, and then find out have the output, and this will give you the coefficient. You know, I know it looks scary. It should be scary for you, but the question is, and the real information is here, that you can compute it. It's pretty standard, you know, algorithm. This is something you should be able to do if you play with linear algebra a bit. But you know, I'd like to show you something more, because I promised you to tell you about overfitting a bit, and this will be a really good, you know, ending of the story of this lecture, because you know, overfitting is something that is really painful for any machine learning process, and I will tell you how to fight with this overfitting and where the overfitting really becomes significant. So imagine that we can let's go back to this. And you see, I told you that I have doubts whether this is the best model, because it fits too much. It's like it memorizes everything. But you know, if you memorize everything, the question is whether you can learn something new. And by learn something new means that, what if you get a data point which is outside the scope, so the testing data? How good you can play it with data you have never seen. And it seems that model that has a problem with overfitting cannot play well. So in that case, we try to pick a slightly more, you know, model which is more less complex. We introduce a little bit more error, but the model is able to learn. Which you have, when you have overfitting, means that, well, but you know, you cannot simplify too much, because you know, we took the first simplification, which is like this, the second simplification, which will be the straight line, which introduce a lot of error. So you know, be aware with the simplification, of course. And now I tell you about the terms of regularization, and we pick two of them. Regularization. It's all about prevention of overfitting. You know, if you introduce a new concept, you have to know how it works, because if you run this from scikit-learn, you can specify which type of regularization you'd like to pick. So you know, our idea is that we'd like to minimize the error, and I told you what we'd like to minimize. You see, this is the case we'd like to minimize. We'd like to minimize that part. So it seems to me that this is something we have no control. This is the data. This is the data. So we can only control that part. But take a look. Right now, it's a vector. You see, it's some kind of, it's not one-dimensional. It's not a scalar anymore. But we call this coefficient alpha. So now what I can do, of course, it should be squared here. Sorry. So what now we can do is we can rewrite the equation using the alpha, but take a look. Our goal should be to minimize the error, and the error is, we'd like to minimize the error, so the error should go to 0. So we introduce so-called loss function. So the loss function should be very close to 0. It's the error definition, yes? So we'd like to minimize this. I can, you know, you can replace the terms because you square them. So in that terms, you have, of course, this part here. And remember that in this prediction, you have this alpha coefficient. So in that case, take a look what's going to happen. You can only control the alpha. So in that terms, if there is, you will see that there is, for example, you predicted this is the actual value in point number 1, and you are trying to, you have predicted something like this in point 1. If the error is big, what you try to do, you try to use alpha to minimize the error. So what you try to do, you try to generate the alpha coefficients, and if the alpha becomes big, I mean it's really greater than 0, it's big one. So you are forcing the you know, the errors to be small. So you introduce a big alpha. This is exactly what overfitting means. So you will end up with very complex alpha vector up to n, and those will be big numbers. So in that case, to prevent this overfitting, there is a lot, sorry, I will tell you first about ridge regularization, which is called L2, and this will be a very simple equation which tells you about how you should minimize. So we know how it is. So that's the actual value. We have this alpha term, and we have, of course, the input vector. This is something we predict, and this is the coefficient here. So you try to also have the square root of the alpha you generate here. So think about it that way. If you generate very high alpha here to minimize the error, this very high alpha becomes also here, which introduces the error. So the alpha will be naturally will be smaller and smaller to prevent the overfitting. So this is the regularization mechanism. So this is rich, and you know the second is the lasso, which is called L1, and the lasso is exactly like this. So you have the same term here, it's here, but you do a plus, and this is something which is sum 1 over from 1 to n, and instead of square, you just have something like this. So you have the absolute value. So you know the lasso seems to have a very interesting feature, which I don't have time to explain you, but I encourage you to check it in the literature, because if you use lasso, which is called L1, if you try to, find the coefficient alpha in lasso, if alpha is close to 0, then if you look at the column, which is so the alpha on the ith column, which is close to 0, then you can remove the column as insignificant. You can remove it from the model. So you can compress your model in the terms that it will have less dimensions. So you know, it's fascinating like this. We entered the world of advanced linear regression. It's more than that, but I hope you now have also information about how those regularization works and why they are introduced, because of the stability of your model. And at the total end, I would like to tell you about R-square adjusted. You know, I told you at the beginning that there is an mathematical equation like this. It's R squared. But I did a small star, and I told you this is only for linear regression when you have something simple like this. So it's like a function of x or a of x. But what if we have situation when we have many variables, we have many columns, then this equation is changed a little bit, and it's called adjusted R square. You will find it in the examples. So it's 1 minus, you have RSS over, remember RSS is the best line, TSS is the worst line, and then there is something like this. This is the number of rows, and it's the number of experiments. And here you have number of experiments minus the number of features minus 1. So those are columns. So if number of columns is smaller, the model is more compact, then the adjusted R square is better correlated. If the number of columns is bigger, then your model is complex and the R square goes down. This is why I told you we'd like to have a lot of experiments, but we'd like to have the less possible number of columns. This is because of this equation. And having said that, that's all. I'd like to thank you for being with me here today, and I'd like to invite you for the next lecture where Sandeep will explain you the state of art of feature engineering. Thank you very much, guys, and have a great day today. Next 24 hours is for you. Thank you. And we have questions. Yes, this is exactly, I have a question from Mr. Submaranian. Take a look. I have the next example, which I show you, which I haven't got time to show you. There is an OLS, which is called, this report is called ordinary least square. And from this report, you can find the line of the best fit. That's true. What's more important, it's a lot of statistics here. You have to take a look into it. So there is a t-statistics, which is just division of coefficient and standard deviation. But the most important, let's say, right now, the most important statistics is this one. So the p-statistics. So if you have a value of p, which is greater than 0.5, so then if the value is greater than 0.5, then you can think about a variable, so the column which is here, which is connected to your input data. So in that case, you can think about removing this column from your model. In that case, your model will be simplified. But you know, it's not that easy, because there is another thing which is called VIF. And in VIF, it's called variance inflation factor, which is in, I will tell you what is the definition. Where is my screen? So, you know, there is, you have to, in OLS, ordinary least squares. So it's a normal, this is the normal least squares linear regression method. So you have to take into p statistics. If p is greater than 0.5 for the input, then you can think, okay, let me remove the input. I don't need it, remove it. But you know, it's not that simple, because you have to think about something more, which is VIF, as I told you. And the VIF is variance inflation factor, which is described as 1/1 minus r square. So in that case, you have to combine those two statistics. And if you find, for example, that this is like this, so you have bigger value of p statistics, and VIF is less than 5, then if you have those two informations, you can think, let's remove the ith, for example, let's remove the ith column. It's not important. We can simplify the model in that case. So that's one of the examples. So yeah, I hope I answered the question. It's more than that. You know, it's like, what I'd like you to do is to read about regression. I will share the Jupyter notebook. I will share this printings I did for you during the talk. And I will share a book I found like a year or two ago. It's free, which is which has a very good chapter about linear regression. It is I think it was written in Stanford. They published it publicly, so we can use it. I use it for learning a lot, and I hope you will like it as well. So yeah, I will share it definitely with you. Which algorithm we can use to forecast capacity on SQL Server? Oh, that's the you know, Devesh, this is something I was also working, you know, quite extensively about capacity on SQL Server. And, you know, it all depends on the workload you have. First of all, let's, if you know, you can think about the data size and log size can be totally different things. So you can measure them separately. So in that case, you can have the number of operations, number of transactions as inputs, and the output is just the size of the data file. So linear regression could be, let's try with something simple, but you know, SQL Server is more complicated than just the linear engine. You have a parameter which is called auto growth, and yeah, it could be a little bit more, you know, in that case, your line will not be like this, but you will have something like this. You will have this kind of quantification. So even if your data size, your real data size is like this, what you measure is something like those steps those quanta of information. So I think it might be a little bit more. Yeah, I was working about capacity of SQL in general case, how we can measure it, and still have no good results. So, and can it be applied to CPU and memory? That's also a very, very good question. And the answer is, you know, the memory, the memory management in SQL is also a complicated engine, how SQL manages memory. And it's correlated with the execution model in SQL. And when you have at least those 3 queues, when you have this runnable queue, so you have the resources and you are waiting for the CPU, then you go to CPU and actually your task is processed, and then you are waiting for resources, so you are on the waiters list. So you would have to take all those informations into consideration as well. And if you think that SQL most of the time is not single-threaded machine but multiple-threaded. So forecasting only based, you know, of the historical data you can measure for queries without going that deep. That's possible. For example, I would start with the data collectors and of course query store. You have a lot of information there. That would be a good point of start. And Elisa, could you explain what nonlinearity means to nonlinear function? You know, it's exact. You can use nonlinear function in the in that case in the here. Those functions can be nonlinear. They are nonlinear, as I told you. So in that case, the entire function is nonlinear. The only linearity you can have are those coefficients, and that's all you can have. Okay, I see Amit on my third screen. I think it's now time to coffee. Sorry, I was talking too much. I can spend entire day talking about this. It's
yes.
So fascinating. I have a lot of more materials here.
You can.
You know, the conference must go on. The show must go on, and probably Sandeep is waiting for the room here. So thank you very much for having me here. It was great time, really great time. I have a lot of fun. And I can't wait for December to be with you once again and talking about quantas, which is my second biggest hobby. So talk to you on December. Thank you very much.
Thank you very much, Damian. Thank you so much.
Have a good day. Bye-bye.
Bye. Take care and have fun.